So hi everybody, thanks very much for coming today. I'd like to thank Liam and Colin for their invitation for us to come and speak today. Pretty much what we're going to have is Harut is going to present geospatial analysis, spatial statistics, basically an introduction to GIS for anybody who doesn't know or hasn't an experience of geographic information systems. And then I'm going to give some preliminary analysis that myself and some colleagues have been doing, applying GIS to social science research. So, thanks very much.
Thank you, Finn. Okay, so today I will give you some brief presentation about geospatial analysis and spatial statistics available in GIS software. In my presentation, I will give you a brief introduction to geographic information systems, basics of spatial statistics, how to measure spatial distribution, how to do spatial pattern analysis, how to run regression analysis in GIS software, and also how to do spatial interpolations. So what is GIS? GIS stands for Geographic Information Systems. It is not just a software, it is the system of computer software, hardware, data, people working with that software, and it allows you to explore, manipulate, analyze, and present spatial information. To say simply, GIS links graphical features to tabular data, which we call attributes in GIS. Concepts are not new. First application of geographic information system was done by Dr. John Snow, a British physician who tried using geographic information to study the cholera epidemic in London in 1854. This is the map he produced during that study. He plotted the cases of cholera in London and he plotted by cross the places of water pumps. As a conclusion, he got that pumps were the source of contagion. Of course, during this time there were no computers and everything was done using paper maps, but the same concepts now are used in GIS software. So how GIS stores data? In order to represent the reality, GIS stores data using several layers. In this example, you can see that we can have layers for counties, cities, schools, homes, streets, and other features. And composition of these layers represent the model of reality in GIS software. Now it is very popular. Almost every industry can use GIS. These are just some industries which are actively using GIS software now. A few examples, like this is earthquake monitoring map for United States. By color, you can see which regions of United States have more earthquakes, more severe earthquakes. Another example is greenness of USA for a particular day. In this map, you can see the food balance in Africa. Again, by color, you can see where there is a food shortage, where there is enough food. A similar map showing water balance in Africa. This example was done during our research. The first map is a land use map for Greater Dublin region in 2006. And then we have used this map to simulate the future map of Greater Dublin region for 2026. Now GIS already converts from personal computers to distributed geographic information services. You all know Google Earth, Google Maps, Microsoft Virtual Earth. There are a lot of other geographic information web-based services also available, like ArcGIS Online, Map Blender. There are many commercial and free products currently, which allows analyze without buying all data and software. Okay, so now let's go into the basic of spatial statistics. What are the spatial statistics? They are exploratory tools that help you to measure spatial processes, spatial distribution, and spatial relationship. There are a lot of different types of spatial statistics. But you should understand that saying spatial statistics, we don't mean the general statistics applied to spatial component, which you usually do during your surveys. Saying spatial statistics in GIS, we mean that GIS use the distance, area, space in their math formulas to calculate spatial patterns of your data. We will focus on two categories of spatial measurements. So the first one is identifying characteristics of a distribution. This tool answers this tool can answer like where is the center of your features. In this map you can see there are a lot of points, and the tool helps you to find where is the center of that distribution. The second category lets you quantify geographic pattern. You can clarify are your features randomly located, are they clustered, or maybe they are dispersed. So why we should use spatial statistics? Spatial statistics is one of the many approaches that can be helped to assess or analyze our data, and it is very powerful. Because with spatial statistics we get better understanding of geographic phenomena. You all know that everything usually happens in some location during some time. So if you are analyzing your data just taking into account time and not location, you are losing some information and you will lose some patterns. Spatial statistics also help us make decisions with higher level of confidence. Of course, you can say my research shows something, but it will be always more evidence-based if you say that statistically we get statistically significant results for something. So using spatial statistics in GIS, you can get this known p-value, for example, or confidence intervals in order to provide more evidence-based information about your results. There are a lot of tools available in modern GIS applications. Particularly in this slide, you can see the toolbox of ArcGIS software, which is one of the most popular GIS software currently used. The good thing that this spatial statistical toolbox is the core part of the GIS software, ArcGIS package. You don't need any additional license, you don't need to pay for it. It is included with the basic package. And another good thing that all tools are provided with their scripts and models. So you can study the formulas, you can even change or modify the formulas based on your requirements. Now let's talk about how we can measure the spatial distribution. When we measure the distribution of spatial features, we are interested in answering a simple question. Where is the geographic center of my features? Which feature is the most centrally located? How are features dispersed around the center? The tool we can use for this kind of analysis is called Measuring Geographic Distribution toolset. It often used to compare distributions of different data sets, to identify directional trends, or examine changes over time. For example, in this map provided in this slide, you can see the graphic where the cases of dengue fever for a village in India is presented. And we wanted to know how the distribution of disease changed during the first 3 weeks after outbreak. Using a standard distribution toolbox from a GIS package, we can get 3 different circles which are representing the distribution of the cases during these 3 weeks. So the first circle shows the distribution of disease in the first week, and we can see that it is the disease started from the low left corner of the region. Then it was spread to wider region in a village, and then finally in the third week, which is the biggest circle, you can see that almost all village was covered by the cases. Another question which we can ask is, where is the center? There is a special tool available in GIS called Mean Center Tool. Actually, it computes the average X and Y coordinates of all features in the study area and create a point which is located in the exact geographic center of your features. But you can have another use of this kind of tool. For example, you can compare distributions of different types of features or track changes in the distribution. In the second map, you can see the same region, California in the United States, but in this case, it shows the change of population center from 1900 till 2000. And you can see that in 1900, population center was really in the central part of California, but during 100 years it moves to the southern part of California. Another question is, what is the most central feature? This is already identifies the most centrally located feature. For example, let's say we want to find the best location of new health center for these 5 towns. There is no need for geographic information system to clarify that the Springfield is the central town and like it can be there, the new health center. But again, the central feature tool will provide this information that the central is Springfield. But more interesting question is, what is the most accessible location of the greatest number of people? In this case, we can use already population information of these cities to identify where is the location where more people can be accessed easily. And using the central feature tool, you can clarify that Bakertown, which has the most population, is more appropriate place for location of your health center. Of course, for 5 cities it seems obvious, but you can take example where you have 100 or 1,000 features and you won't find similar central features. While the mean center and central feature tools tells us about the central of distribution, they don't tell us about the overall distribution. The standard distance tool tells us how dispersed our features are around the center. In the map shown, we have indices for respiratory disease among children. We want to see if we can detect any seasonality in this disease. So by green circle, you can see the cases which happen in spring, and by blue, you can see the cases which happen in winter. The bigger the circle, the more dispersed is distribution. So you can see that in winter, we have widely affected region. Using distributional tools, you can also get trends of your distribution. For example, you can compare distribution, examine different time periods, show compactness and orientation. In this map, it is shown the distribution of different population ethnicity groups. And you can see how they are distributed, the trend. This is another example showing the special pattern of piracy near Somalia. Okay, now let's talk about our next category of spatial statistical tools, spatial patterns analysis. These tools give us a way to measure the degree to which our features are clustered, dispersed, or randomly distributed across the study area. When we talk about analyzing patterns, we are interested in finding out if there are underlying spatial processes influencing the location of our features. Are our features randomly located throughout the study area, or they are displaying clustering or dispersed pattern? In this example, we have relative per capita income for New York from 1969 to 2002. The question we may ask, are rich and poor becoming more or less spatially segregated? Using these thematic maps, it is difficult to answer such kind of question. But we can run spatial autocorrelation or global Morans tool from ArcGIS, and we can plot the score of z-scores from the tool, which reveals trends over time. In the graph, you can see the drop, which indicates a decrease in the rich-poor spatial segregation. In the previous slides, we asked the global question, is there clustering? Now we are going to switch the gears and ask a local question, where are the clusters? Or where do features with similar attribute values cluster spatially together? One of such tools is called hotspot analysis. It indicates the extent to which each feature is surrounded by similarly high or low values. Very useful in crime prevention, locating target markets, finding the source of an epidemic. For example, In this map, we have hotspot analysis, which was run to show if there are persistent areas in the United States where people are dying earlier or living longer than the average American. By red areas, you can see statistically significant early death hotspots for 20 years, and the blues are statistically significant cold spots with early deaths. Saying cold spot which means that in these areas there are no much cases of death for for young population. Another example is the call to emergency services. Here you can see again by red the areas where many calls, and by blue the cold spot areas where there are no much calls. And you can overlay this information with the location of your response stations, which are marked by crosses, green crosses here. This will allow you to understand, are these response stations located in the most efficient places? For example, the left corner, bottom corner one is in a cold region where there are no many calls, and maybe it will be more beneficial to move it to red areas where there are a lot of calls. Now let's speak about regression analysis option in GIS. So till now we have used pattern analysis to show are there places where people die young, where are the test scores consistently high, where are 911 emergency call hotspots. But regression analysis will help us to answer why questions. Why are people dying young? What factors contribute to consistently high test scores? Which variables predict 911 emergency call volumes? You all probably have used and know the regression analysis, and this is just to remind the main terms and concepts. We have dependent variable in the left side, and then we have explanatory variables and coefficients and random error in the right hand side. So the regression analysis get the coefficients, and by sign and magnitude we have the reflection of any explanatory variable relationship to the dependent variable. Using ArcGIS regression analysis, you can get the same parameters and coefficients and similar information as you usually do running by SPSS or other statistical packages. But in ArcGIS, you have two different versions of regression analysis. The first one is ordinary least square regression, which is the general regression you all know. The second and unique one is geographically weighted regression. So what is the difference? For ordinary least square regression, you have global regression model. One equation calibrated using data from all features. Relationships are fixed. But for geographic weighted regression, we have local regression model. It composes one equation for every feature, calibrated using data from nearby features. Relationships are allowed to vary across the study area. You will understand this in the later slides where I bring the example. So let's study an example where we have people dying young in some region in the United States. You can see the circle, which is South Dakota. So the question is, why are people dying young in this region? For the first hypothesis, we will run our general regression model, and we will try to use only poverty as an explanatory variable to see if poverty is the reason of dying young. Running the regression analysis in ArcGIS, we get information, particularly that adjusted R-square value is about 66%, which is not bad if we take into account that we have got just one explanatory variable. However, significant spatial autocorrelation among model residuals indicates important explanatory variables are missing from the model. So we will continue our research, we will do some exploration, we will discuss this with other people, and we will find other parameters which can be introduced into our regression model. As a result, we have got more correct regression model. If you take into R-square value here, Yeah, we have already 86% explained by our variables. And there are other 6 parameters which we usually check to be sure that our regression model is correct. Like we should have coefficients with expected sign. No redundancy among model explanatory variables should be. Coefficients should be statistically significant. Residuals should be normally distributed. And of course, R-square should be high enough. And residuals are not specially autocorrelated. However, in ArcGIS, you get one more parameter which shows you if there is a difference in different parts of your region. The parameter is called co-anchor statistics, and if it is a significant, like we have here, you can say that geographically weighted regression will produce better results because there is some variation of parameters in the region. Okay, so we will try now geographically weighted regression to see if we can improve our results. In general, geographically weighted regression gives us similar output. We can get R-square. In this case, we can get R-square already higher. In this table, if you take the last number, it's already 89%. So already we have some improvement in our model. We can have residual maps showing model under or over predictions, and you should be sure that they are not clustered to have good model. And this is what is unique in geographic weighted regression. It gives us coefficient maps which show how model relationship vary across the study area. Because, for example, if we are taking like the car accidents as an explanatory variable for dying young, it can be in one region car accidents has very big influence on dying young, but in another region it is not so important. There are not so many people have accidents. And this is when geographic weighted regression is very powerful. It shows you the value maps of coefficients where you can see in which region that particular coefficient has most influence. And finally, it gives us the other parameters like model predictions, residuals, standard errors, coefficients, and condition numbers. Okay, and in my final topic, I will show you how you can use spatial interpolation in GIS. What is interpolation? Using interpolation, we can estimate an unknown value from known samples. Based on spatial autocorrelation and dependence, we can get the degree of relationship between near and far objects. This is very helpful, especially when you are getting some samples in a region and you want to get it interpolated for a whole region. The most basic way to do interpolation is using linear interpolation in GIS. In this example, you can see 2 points which we can assume that are rainfalls between 1 and 2 stations, and they are apart 1 mile. Using linear interpolation, you can get rainfall in the middle of these 2 stations, like 1.5 in this case is the value obtained by interpolation. But there are more sophisticated methods to interpolate data in ArcGIS. These are just a few available methods which you can use. And there is also a way to conduct sample points in the interpolation method. There are 2 methods to control the search radius. One is the variable method, which expands to find minimum number of samples, which means you give minimum number of samples in order to calculate the value in the middle of the sample. And the other way is to use fixed method, which use sample found in the specified radius. So in this case, you give just the radius, which should be used in order to estimate the value inside of that, in the center of that circle. If you run different interpolation methods for the same data, you may get different results. Like here, you can see 3 different interpolation methods. Of course, the pattern is similar, but there are a lot of differences. There is no way to say which one is better, which one is worst. But you can decide to use interpolation method based on the characteristics of your data. If you know nothing about your data, in that case, it's better to use natural neighbors method, for example. It is the most conservative, assumes all highs and lows are sampled, will not create any artifacts. Your input data is contours, for example. In that case, you can use topo to raster tool. If you know that the highs and lows are not sampled, you can use spline. So there are a lot of characteristics which you can use and then decide which interpolation method is the best. Finally, there are many resources available currently to study these all methodologies which I presented. You can use guides, you can use books, for example, very good book by Fortingham, Branson and Charlton about geographic weighted regression. There's free web courses in the virtual campus from YES3. There are good magazines from YES3, and of course ArcGIS web help also very useful. Finally, UCD Urban Institute has a lot of data available for UCD researchers. We call our dataset URBIS. We have data about administrative boundaries, places, heritage and protected areas, land cover datasets, about transport, water bodies. We have CSO census data. We have geodirectories from 2005 to 2008. And we have some satellite images also. And we provide also support for this software which is available in Urban Institute. The most popular is again ArcGIS, but there are other GIS and free GIS software also like GRASS. And we also provide GIS training courses. We have 2 courses, introductory and advanced. And we also provide some consultancy and assistance for projects or proposals. That's all. If you have any questions, please.
So if I just got some, I mean, I've never used this stuff before, but if I just got, like, say, you know, unemployment data from the CSO and I wanted to just have a go at this, so it'd be fairly, I can download ArcGIS from. Yep,
for UCD campus use, you can use the license provided by UCD. Why I'm saying campus? Because you should get connected to network from campus in order to get license. It is based on network. You can download ArcGIS software from your account. If you go to software downloads in your account, you can get ArcGIS software there. And if you have tabular data, like you have mentioned, the census information, you need also the map in order to connect this tabular data in GIS. The maps are available in our institute, like ED boundaries or counties or other administrative units. So what you need just to link your tabular information with map, and then you can use all data provided in your tables using GIS software. No more questions? Okay, thank you. Then I will give the presentation. By the way, I have